We're going to have a look at worksheet number 8. We had 2 questions for homework last night. It was questions 4 and 5. So we're going to do both of those, starting with number 4. This one says an airplane is traveling east at an airspeed of 150. So this is where it's trying to go. This is where it's heading. I shouldn't say where it's trying to go. This is where it is heading, where it's aiming. East at 150 meters per second. Is that a solid line vector or a dotted line vector? If I'm heading east. What is it? Huh? That's a solid line vector, right? That's contributing to where this airplane actually goes. It's not where the airplane actually goes, just contributes. So I'm going to draw that as a solid line vector, make it 150 meters per second. Now there's a 30 meters per second wind blowing to the north. That wind is not where the airplane goes either, but this wind does contribute to where the airplane goes. When you combine how fast this plane can travel in still air and combine that with the wind velocity, then that's when we get where we actually end up going. So let's combine 2 solid line vectors to make one dotted line vector. That dotted line vector is drawn from start to finish. We solve for that value of r, and that gives us our final speed, our magnitude of our final velocity, right, Nick? We're going to say r is equal to 150 squared plus 30 squared, and we're going to say theta is equal to the inverse tan function of 30 over 150, or opposite over adjacent. So let's get the value of r here first. Let's say r is the square root, bracket 150 squared plus 30 squared, gives me a value of 152.97, or we're going to actually just round that to 2 digits, 1.5 times 10 to the 2 meters per second. And the angle, theta, we expect to get here, what, a big angle or a small angle? It's going to be a small angle because it's only 30 up over 150 over. The inverse tan of 30 over 150 gives me a value of 11 degrees. We're going to say that's 11 degrees north of east. 11 degrees north of east. Now, let's just take a step back from this and think about it logically for a second, not mathematically. Okay, if we've got an airplane that's aiming to the east, but there's a wind going to the north, where am I going to end up going? Somewhere north and east, right? So does this answer that we get make sense? Does it seem reasonable? Yeah, there's no guarantees there that that's the correct answer, but at least it's reasonable. If you get south of east, well, then you know you've done something wrong, because you're not going to be aiming to the east, have a wind to the north, and end up somehow going southeast, right? So stop and look at your answer. See if it's reasonable. Okay, it doesn't guarantee correctness, but at least it gives you a lot more confidence in that. Sometimes it shows you that never tells you you're right, but it sometimes tells you you're wrong if you see your answer isn't reasonable. Okay, we had one more question, and this one I think is harder than the first one we just did. This one says, the captain of a ship aims his ship with a velocity of 25 meters per second directly north across the river. Current flow is 8 meters per second to the east. The river is 850 meters wide. We're going to find the velocity of the ship relative to the shore, first of all. All right, the captain aims his ship 25 meters per second directly across the river. That is a solid line vector, because that contributes to where the ship goes. The ship doesn't go north, the ship aims north. There's a river current to the east that is 8 meters per second. That also contributes to where this boat goes. Now, where does the boat actually go, or what is the velocity of the ship relative to the shore? That's going to be the sum of those vectors. The sum of those vectors, not 25 plus 8 is 33, but rather the square root of 8 squared plus 25 squared. Okay, let's get that value, and let's get theta. R is the square root of 25 squared plus 8 squared, gives me 26. I'm going to write down the unrounded number here to 3 or 4 decimal places, because there is a B and a C, and I don't know yet if I'm going to have to use this number later on. If I do have to use it later on, I want to use the unrounded, the non-rounded number, rather than the rounded answer. So we're going to say 26.249 meters per second, which will now turn around and round to 26 meters per second. Still got the unrounded number there if I need it, though. Theta is the inverse tan function of opposite over adjacent. What's the opposite? Is it 25 or is it 8? 25 or 8? Megan, 25 or 8, opposite sides? 8, good. So it's 8 over 25. We should expect to get big angle or small angle here? Evan, big angle or small angle, do you think?
Small.
Yeah, it's going to be fairly small. When the top number is quite a bit smaller than the bottom number, then you're going to get a pretty small angle here. So let's say it's the inverse tan of 8 over 25. Gives me 17.7 degrees, 17.745. Or we'll round out to 2 digits, 17 degrees. Now, how do we express that? 17 degrees what of what? Oh, sorry, no, it should be 17, should it? I just saw that look on Megan's face, like, what is he doing? It's not 17 degrees, it is 18 degrees, right? And how would we express that? 18 degrees?
East of north. Sorry.
It is east of north. Yeah, it is east of north because we're measuring that angle from the north. Okay, we're measuring that angle from the north there. All right? Okay, there's question A. Now, what about B, the time that it takes the ship to cross the river? Here I'm going to draw the river. Okay, there's my river. And the river is 850 meters wide. So I'm going to label that as well. Don't label that on your vector diagram because that's for velocities, but label it somewhere. Now, you want to find the time that it takes the ship to cross the river. We're going to use, as you guys told me yesterday, the equation V is equal to delta D over delta T. We're going to rearrange that to solve for time. T goes up by multiplying. V times T is equal to delta D. And then the V goes down by dividing. I get delta T is equal to delta D over V. Now, here's what you got to remember for this question. Delta D, the displacement, and the velocity in this equation always must be in the same direction. Got it? If you've got a displacement to the right, then the velocity is to the right. If you've got a displacement down, then the velocity is down. If you've got a displacement at 32 degrees, then your velocity is at 32 degrees. Got it? Velocity and displacement have to be in the same direction, always. All right, if I'm going to use this 850 meters across as my displacement, then what velocity do I need to use? Keeping in mind that my velocity and displacement must be in the same direction. If I'm using 850, then I'm going to use what for velocity? Jen, what do you want to use there? The 25, the 8, or the 26? 25, yeah, because the 25 is straight across, as is the 850. Does that make sense? You could, like, this would not make a lot of sense to do, but you could use the 26.249 meters per second right here if you found that displacement as well. That would work. But it would be a lot more work than you need to do because we already have a displacement and a velocity that are in agreement with each other, the same direction. So let's say 850 divided by 25. I think that works out to be 34, isn't it? 34 seconds. And it is exact, I think, right? Yeah. Now, question C asks how far downstream. So we're looking for how far downstream does the ship end up when it touches the other side. We're also going to say V is equal to D over T for this one, but rearrange this one and solve for D. I get D is equal to V times T. Now, I want to find out a displacement horizontal. What velocity do I want to use? 25.8 or 26.2? If I want to find a horizontal displacement, then I'm going to use the 8 meters per second, the horizontal velocity. So it's 8.0 times a time of 34 seconds, and 30 times 8 is 240, 272, I want to say, 272 meters, which are going to round to 2 digits, or 2.7 times 10 to the 2 meters. Good? So I use the y velocity with the y displacement. I use the x velocity with the x displacement. I could have solved for the angled displacement and used it with the angled velocity. It just wouldn't have made a lot of sense to do that because it would have been a lot of extra work. You guys okay with that? Okay, I got one more example problem that I want to give you with this before we move on to the next topic. One more question on your worksheet that I want to have you work on with this. And then we'll move on to our last topic of the unit, which is projectile motion. Take a look at this example, number 19. It's the third to last example in your unit. It says the pilot of a plane wants to head north. We want to go north. It doesn't say we're going north. It says we want to go north. At a speed of 200 meters per second. But there's a wind of 20 meters per second blowing to the west. Now, what's the velocity and the angle that the pilot must aim the plane? I don't know about you guys, but I think that first vector is kind of tricky to work our head around. The pilot wants to head north at 200 meters per second. Solid line or dotted line? It sounds like it's a solid line, right? We want to go there, but it isn't. It's a dotted line. Let's assume for a second that where the pilot wants to go, the pilot ends up going. Does that make sense? It doesn't say we're aiming here. It just says this is where we want to go. So let's assume that we're able to go where we want to go. That would make it a dotted line vector. But in the absence of that logic, take a look at your next two vectors. Sometimes this happens to all of us. We run across something that's like, that doesn't really make sense to me. What's the strategy that we can follow? Well, keep reading and see if there's anything that kind of clarifies it for you. Okay, if this sentence right here doesn't really make a whole lot of sense, whether that's solid or dotted line, keep reading. The wind to the west, is that solid or dotted? That's solid because that contributes to where I go, right? Okay, good. Where I aim, is that solid or dotted? That's solid because that contributes to where I want to go, right? To where I go. So if the wind contributes to where I go in solid, and where I aim contributes to where I go in solid, what's left? Well, it must be dotted then, right? So we said that it was dotted because we're assuming that the pilot goes where he or she wants to go, but by process of elimination, it has to be dotted. Has to be. So let's draw this now. It's a little bit trickier to draw this one. The pilot of the plane wants to head due north. We're drawing my resultant vector first this time, 200 meters per second. Now there's a wind of 20 meters per second to the west. I'm drawing that as a solid line vector. Where am I going to draw that? Where am I going to draw that? Position 1, position 2, position 3, or position 4? 1, 2, 3, 4. Yeah? We could draw it, no, not at position 4. If we try drawing it at position 4, look what happens. That's head to tail, but the resultant vector should not be drawn head to tail, right? Does it make sense? So what? You can make it 3. It's actually easier to if you make it position 2, but 3 would work as well. I want to make it position 2 here. All right, so we got a wind that's to the west. Where's my other solid line vector? Well, it's going to be up here, so that it's drawn head to tail. Now this diagram is a little bit different because although it's a right angled triangle, my resultant vector is not my hypotenuse. My resultant vector is A. I'm looking for not the resultant, I'm looking for the speed at which I aim. We'll just call it V, the speed at which I aim. Now we're going to solve for it in the same way. We're going to say V is equal to the square root of 200 squared plus 20 squared, and theta is equal to the inverse tan function of opposite over adjacent. That's 20 over 200. We should end up with a pretty small angle there again, right? Square root of 200 squared plus 20 squared gives me a value of 200.9, or just 2.0 times 10 to the 2. And theta is the inverse tan function of 20 over 200. This is going to give a really small angle, I think. Yeah, 5.7 degrees. And this would be 5.7 degrees east of north. Yep.
We're not calculating the hypotenuse. Shouldn't it be the hypotenuse squared minus the other?
We are solving for the hypotenuse. Okay, we're still solving for the longest side of the triangle. We're just not solving for the resultant. Does that make sense? No, that's a good question, though. That's a really good question. Sometimes we look at this and think like, oh, sometimes we make the hypotenuse and the resultant vector synonymous with each other because every time so far, that's what it's been, right? This time it's not. The hypotenuse is still the longest side, but it's not the resultant vector. The good news is I'm still solving for the hypotenuse, so I'm still going to mathematically do it the same way. We're just calling it something different now. Now, let's see, does this make sense? Okay, we want to go north. We want to go this way. But there's a wind blowing to the west, this way. Where do I have to aim? If I want to go north, but there's a wind going west, I kind of got to aim northeast somewhere, don't I? And that's exactly what I got, 5.7 degrees east of north. Does that seem like a reasonable answer? Yeah. Yeah. Yeah, so no, exactly. You're not going to aim southeast if you want to go north and there's a wind to the west, right? So the danger that sometimes we fall into is that we think we can solve these questions using logic. We can't. We can check our answer using logic to see if it's reasonable, but we can't get our answer using logic. So don't skip steps. Do the work. Draw the pictures. Draw the arrows on the pictures. Make sure that the solid line vectors are drawn head to tail. Do all of that stuff, and then just use your logic to check your answers, as opposed to actually get your answers. And even then, it's not a perfect check. It's just a, is it reasonable kind of check. All right, I'd like you guys to take a look here now at worksheet number 8 again. This time, it's going to be question number 6. Let's go over question number 6 now. It says the captain of a ship wants to go directly south. Wants to go, that's going to be a dotted line vector because we're going to assume that the captain of the ship actually goes south. So we're going to say dotted line vector to the south, 15 meters per second. There's a river current that's 5 meters per second to the east. Where am I going to draw that 5 meters per second river current here? Position 1, 2, 3, or 4? Yep. Position 2, we could draw in position 2, absolutely. Is that right? Yep, we could draw in position 2. Tell you what though, I'm not going to draw it in position 2 because if I draw it in position 2, it makes the angle harder to see. Okay, we can still calculate it, but it's a little bit harder to see. My suggestion would be draw it so that it's head-to-head. Tail-to-tail works, but you're going to see that when we draw it head-to-head, it's easier to find the angle. Does that make sense? So that's 5 meters per second. Now, where do we have to aim? It's going to be down this way. We're going to solve for that value v. Now, if we had have drawn it the other way around there, Aoife, it would have been absolutely correct. Okay, and we would have solved for this, right? But this is the angle that you would have had to find, and it's a little weird finding that angle when it's not at the beginning there, right? Yeah. So it's easier to draw it when it's head-to-head like this, and then we can see that the angle is just at the beginning. Okay? Yep. Let's finish this way, and then we'll take a look at that. 5 squared plus 15 squared. What does that end up being, 5 squared plus 15 squared? Yep. 15.8 meters per second. We're going to round that to 16 meters per second, 2 digits. And theta is the inverse tan of opposite over adjacent. 5 over 15 gives me, that's going to give you a small angle again. What's that give me? 18.4 degrees. Okay, so we'll say 18 degrees. And we'll make that west of south. So you want to go south, but there's a river current to the east. Where do you got to go? Somewhere south and west, right? Had you drawn it the other way, the way that we first started drawing it, we would have gotten 72 degrees south of west, but it would have been harder to see where to label that angle. We could have done it. We could have done it right. It just would have been harder. Okay, Nick, what was your way? Okay. Okay, watch it, because sometimes we do something wrong and we get a right answer, right? That's great. But we want to make sure that we understand how to do it the right way, because if you do it the wrong way and get the right answer, it means you got lucky, right? And we're not going to get lucky every time with it, right? If we do it the right way every time, we'll get the right answer 99 times out of 100, right?